You're standing in your kitchen, staring at a pot of water on the stove. You turned the heat on 5 minutes ago, maybe more. The burner glows red beneath the metal, heat radiating into the air, energy flooding into the water molecule by molecule. And yet nothing. The surface remains smooth, glassy, perfectly still, not a bubble. Not even a shimmer. You know it's going to boil, physics guarantees it. Thermodynamics demands it, but in this moment, watching, waiting, it feels like the universe has conspired to keep that water stubbornly, impossibly still. Every second stretches. Your attention sharpens, zeroing in on the pot with laser focus, searching for the first sign of movement, the first tiny bubble that will vindicate your patience. But the more you watch, the longer it seems to take. Time itself appears to slow, to thicken, as if your gaze has somehow reached into the fabric of reality and pressed pause. You've heard this saying 1,000 times. A watched pot never boils. It's a cliché, a piece of folk wisdom passed down through generations, meant to teach patience, to remind you that obsessing over something doesn't make it happen faster. But here's the thing, what if it's not just a metaphor? What if there's something deeper, stranger, more fundamentally true about that statement than anyone realizes? What if, in some very real sense, your act of watching is interfering with the process, not just in your perception of time, but in the actual progression of events? What if observation, the simple act of paying attention, has the power to freeze reality in place? This isn't mysticism. This isn't New Age wishful thinking about consciousness creating reality. This is quantum mechanics, and the phenomenon has a name, the Quantum Zeno Effect. Named after Zeno of Elea, the ancient Greek philosopher who proposed paradoxes about motion and time, the Quantum Zeno Effect describes a situation where continuous observation of a quantum system prevents that system from changing. You watch something closely enough, frequently enough, and it stops evolving. It freezes, not metaphorically, literally. And while this effect operates at the scale of subatomic particles, far removed from boiling water and everyday experience, the principle it reveals is so bizarre, so counterintuitive, that it forces us to rethink what we mean by observation, measurement, and the role consciousness might play in the unfolding of reality. Let's start with the psychology, because that's where most people's experience of the watched pot lives. When you stand over that stove, staring at water that refuses to boil, time genuinely feels slower. This is not an illusion in the sense that you're reimagining it. Your brain is actually processing time differently based on how you're reallocating attention. Psychologists call this prospective timing, the way we estimate how long something is taking while it's happening. When you're engaged in something stimulating, varied, attention-grabbing, time flies. Your brain encodes fewer distinct moments because everything blurs into a continuous flow of activity. But when you're waiting, when you're focused on a single unchanging stimulus, your brain encodes every second in excruciating detail. You notice the lack of change. You mark each moment as distinct, separate, dragging. And because your brain is logging more individual moments, the subjective experience of duration expands. A minute feels like 5 feels like 20. The pot sits there, mocking you, and time becomes a weight pressing down on your awareness. But that's just perception, right? The water is still heating at the same rate. The molecules are still gaining energy, jostling faster, approaching the threshold where they'll transition from liquid to gas. Your staring doesn't change the physics, or does it? Because here's where the story takes a turn into the deeply strange. At the quantum level, observation isn't passive. It's not like shining a flashlight on something to see it better. In quantum mechanics, the act of measurement fundamentally alters the system being measured. Before you observe a quantum particle, it exists in what's called a superposition, a probabilistic haze of multiple potential states all happening at once. It's here and there spinning this way and that way, occupying a cloud of possibilities. But the moment you measure it, the moment you interact with it in a way that extracts information, the superposition collapses. The particle chooses one state and locks into it. And if you keep measuring, keep observing, you keep forcing it back into that same state over and over again, preventing it from evolving into something else. This is the Quantum Zeno Effect, first theorized in 1977 by physicists George Sudarshan and Baidyanath Misra. They realized that if you observe a quantum system frequently enough, you can effectively freeze its evolution. Imagine a radioactive atom that has a certain probability of decaying over time. Left alone, it will eventually decay. Quantum mechanics predicts this with statistical certainty. But if you measure whether it has decayed every microsecond, checking again and again and again, and then something bizarre happens, the probability of decay drops towards zero. The atom, caught in the act of being observed, never gets the chance to transition into the decayed state. It's as if each measurement resets the clock, pulling the system back to its starting point before it can change. The more you watch, the less it evolves. Observation, in this context, is a kind of temporal cage. Experiments have confirmed this. In 1990, researchers at the National Institute of Standards and Technology in Colorado trapped beryllium ions and subjected them to continuous measurement. Under normal circumstances, these ions would undergo a quantum transition between energy states at a predictable rate. But when the scientists measured the system rapidly and repeatedly, the transition slowed dramatically. In some cases, it stopped altogether. The ions were frozen in their initial state, unable to evolve, held in place by the sheer weight of observation. This wasn't a fluke. It was an experimental error. It was a direct demonstration that measurement, conscious or not, since the observer in quantum mechanics doesn't require human awareness, just interaction with a measurement apparatus can inhibit change at the most fundamental level of reality. So what does this have to do with your pot of water? On the surface, nothing. The water molecules in your pot are not quantum particles in superposition. They're governed by classical thermodynamics, not quantum uncertainty. Your staring at them doesn't collapse their wave functions because they do and have meaningful wave functions. At that scale, quantum effects average out into predictable, deterministic behavior when you're dealing with trillions upon trillions of molecules. The water will boil whether you watch it or not, and it will boil at the same rate, governed by heat transfer and vapor pressure and the laws of thermodynamics that do and care about your attention. But, and this is where it gets philosophically dizzying, the Quantum Zeno Effect reveals something profound about the nature of observation itself. It tells us that at the deepest level of reality, the act of looking, of measuring, of interacting with a system to extract information, is not neutral. It has consequences, it shapes outcomes. And while those consequences are mostly confined to the quantum realm, the principle they expose, that observation and evolution are entangled, that watching something can prevent it from changing, casts a long shadow over how we think about time causality and the role of consciousness in the universe. Here's the uncomfortable thought. If the quantum Zeno effect works at the smallest scales, where does it stop? Quantum mechanics is the foundation of everything. The classical world we experience, solid objects, flowing time, predictable cause and effect, emerges from quantum processes. It's a question of scale, of averaging, of countless quantum events summing into macroscopic behavior. But the boundary between quantum and classical is fuzzy, contested, not yet fully understood. There are experiments suggesting that quantum effects can persist in larger systems than we thought possible: quantum coherence in biological molecules, entanglement in relatively warm and messy environments. So while you're staring at a pot of water doesn't trigger a quantum freeze, the fact that observation can freeze anything at any scale should make you pause. It should make you wonder, how much of reality is contingent on whether or not it's being watched? And then there's the subjective experience, the psychological layer sitting on top of the quantum weirdness. You stand there, watching the pot, and time slows. Not because of quantum mechanics, but because your brain, hyper-focused on a single unchanging stimulus, is stretching every second into subjective eternity. The pot will boil at the same rate whether you watch or walk away. But if you walk away, time will collapse. You'll check back in 5 minutes and find it boiling, and those 5 minutes will have passed in what feels like an instant because your attention was elsewhere, doing something else, encoding fewer distinct moments. The watched pot never boils isn't about the pot. It's about your experience of time and how attention warps duration. The pot boils just fine. It's you, the observer, who changes. But the echo of the quantum Zeno effect lingers, doesn't it? Because even though the mechanisms are different, psychological versus quantum, the theme is the same. Observation matters. Watching something changes your relationship to it, whether that change is in your perception or in the actual state of the system being observed. And that raises a question that physics and philosophy have been wrestling with for a century. What is an observer? In quantum mechanics, an observer doesn't need to be conscious. It doesn't need to be human. It's just any interaction that extracts information. Any coupling between systems that collapses a superposition into a definite state. A photon hitting a detector. A particle colliding with another particle. Observation, in this technical sense, is woven into the fabric of physical interaction itself. But we are observers in a richer sense. We're conscious. We experience. We don't just collapse wave functions, we feel the passage of time, we assign meaning, we construct narratives around what we see. And when we watch something, waiting for it to change, we're not just measuring. We're hoping, anticipating, projecting our will into the future, as if attention alone could summon the outcome we desire. And maybe, in some infinitesimal way, it does. Not because consciousness is magic, but because consciousness is embedded in the physical world. And the physical world, at its most fundamental level, is strange beyond comprehension. Think about the last time you were waiting for something. Not just a pot of water or anything, a text message, a job offer, test results, a delayed flight. That agonizing stretch of time where all you can do is watch, wait, check, refresh, stare at the screen or the clock or the door, hoping for change. Time crawls. Every minute is a small eternity. And the moment your attention shifts, the moment you get distracted, absorbed in something else, time snaps back to normal speed. Suddenly hours have passed and you barely noticed. The waiting felt longer than the actual duration because you were present for it, marking every second, encoding every moment of non-change into memory. But the moment you stopped watching, time became fluid again, slipping past without weight. This is the human experience of the Quantum Zeno Effect, translated into psychology. You can't freeze a boiling pot by staring at it. But you can freeze your own experience of time, trapping yourself in a subjective eternity where change feels impossible, because your attention has locked onto a single point, refusing to let go. And the irony, the cruel joke at the heart of this, is that the best way to make something feel like it's happening faster is to stop watching, to let go, to trust that the process will unfold without your surveillance. The pot will boil. The message will arrive. The flight will land. But if you stand there, eyes locked, attention clenched, you'll experience every second of the wait, and it will feel like forever. So the ancient saying is right, in a way. A watched pot never boils, not because observation prevents boiling, but because observation transforms time. The pot boils at the same rate regardless. But you, the watcher, the one trapped in the subjective stretch of prospective timing, experience a different reality. For you, the pot takes forever. For you, time stops. And in that sense, the pot never boils, because never isn't about objective duration. It's about subjective experience. It's about how long forever feels when you're the one doing the watching. And beneath it all, hidden in the quantum foam, the Zeno effect waits, reminding us that at the smallest scales, watching really does stop change. That observation and reality are tangled together in ways we still don't fully understand. That the act of measurement is not passive, not neutral, but an intervention, a disruption, a force that shapes the world it seeks to reveal. You're not just a witness to reality. You're a participant. And every time you watch, every time you measure, every time you pay attention, you're reaching into the fabric of existence and leaving your mark. The water will boil eventually. But not, it seems, while you're watching. Let's go deeper. Let's talk about what the Quantum Zeno Effect actually means, how it works, and why it should unsettle you more than the simple fact that staring at water makes time feel slow. Because once you understand the mechanics, once you grasp what's happening when observation freezes a quantum system, you start to see the cracks in the reality you thought was solid. You start to wonder whether the universe operates on rules that make sense, or whether it's held together by something far stranger, something that responds to being watched, something that refuses to change when you're paying attention. First, let's clarify what we're talking about when we say quantum system. At the everyday scale, macroscopic, classical, the world of boiling water and falling apples things behave predictably. Objects have definite positions, definite velocities, definite states, cause leads to effect in a nice, linear, deterministic way. You turn on the stove, heat flows into the water, the temperature rises, and eventually the water boils. Simple, reliable, you can close your eyes, walk away, come back 10 minutes later, and the process will have unfolded exactly as physics predicts, regardless of whether anyone was watching. But zoom in. Shrink down to the scale of atoms, electrons, the fundamental building blocks of matter and energy. Here, the rules change. Particles don't have definite positions or definite states until you measure them. Instead, they exist in what's called a superposition, a quantum limbo where all possible states coexist simultaneously, each with its own probability. An electron isn't here or there, it's everywhere it could possibly be, smeared out into a cloud of probability until something forces it to choose. That something is measurement, observation, interaction with the environment in a way that extracts information about the system's state. When you measure a quantum system, say, you check whether an electron has spin up or spin down. The act of measurement collapses the superposition. The electron, which was both up and down simultaneously, suddenly becomes one or the other. The wave function, the mathematical description of all those probabilities, collapses into a single definite outcome. And this isn't because you didn't know which state it was in before you measured. It's because it wasn't in a definite state. It was genuinely in both states at once, and measurement forced it to decide. This is already weird enough. But the Quantum Zeno Effect adds another layer of strangeness. Because it turns out that if you measure a quantum system repeatedly, rapidly, continuously, you can prevent it from evolving. You lock it in place. Here is how it works. Imagine you have a quantum system that's trying to transition from state A to state B. Left alone, quantum mechanics says this transition happens over time, governed by the Schrödinger equation, which describes how wave functions evolve. The system starts in state A, and over some period, microseconds, milliseconds, however long, it gradually shifts into state B. This transition isn't instantaneous. It's a smooth, continuous evolution through a superposition of A and B, with the probability of being in B increasing as time passes. But now imagine you measure the system after a very short time, so short that it barely had any chance to evolve toward state B. When you measure, you collapse the superposition, forcing the system to choose between A and B. And because it's only been a tiny fraction of a second, the probability of finding it still in state A is overwhelmingly high. So you measure, the wave function collapses, and the system is back in state A fully, definitively. Now you wait another tiny fraction of a second and measure again. Same thing still, and a measure again. A. Again. A. Each measurement resets the clock, collapsing the system back into its starting state before it has time to evolve. The transition from A to B, which would have happened naturally if you'd left the system alone, is prevented by the sheer frequency of observation. You've frozen the system in state A, not by doing anything to it directly, but simply by watching too closely, too often. This is the Quantum Zeno Effect, and it's been confirmed in multiple experiments. One of the most famous was conducted in 2001 by researchers at the Weizmann Institute of Science in Israel. They used a system of ultracold atoms and subjected them to continuous measurement while the atoms were supposed to be tunneling between two quantum states. Quantum tunneling is a process where particles pass through energy barriers they classically shouldn't be able to cross. Pure quantum weirdness. But when the researchers increased the frequency of measurements, watching the atoms more and more closely, the tunneling rate dropped. At a high enough measurement frequency, tunneling stopped almost entirely. The atoms were frozen in their initial state, unable to evolve, held in place by observation. So here's the unsettling part. Observation at the quantum level isn't just about gaining information. It's an intervention. It's a disruption. Every time you measure, you're not passively recording what's already there, you're forcing the system into a definite state, collapsing possibilities, resetting the evolution. And if you do this fast enough, you don't just observe the system, you control it. You stop it from changing. You trap it in a single state, not by applying force or energy, but simply by looking. Now, does this mean you can freeze boiling water by staring at it? No, absolutely not. The Quantum Zeno Effect operates at the quantum scale, and macroscopic systems like pots of water are composed of so many particles, undergoing so many interactions, that quantum effects wash out into classical behavior. The water molecules are in a superposition of boiling and not boiling, they in a definite state governed by temperature, pressure, and energy transfer. Your staring doesn't collapse their wave functions because, at that scale, there's no coherent wave function to collapse. The quantum effects are there, hidden in the underlying structure of reality, but they average out, smooth out, become invisible. And this is the philosophically dizzying part, that the boundary between quantum and classical isn't as sharp as we once thought. There's growing evidence that quantum effects can persist in surprisingly large, warm, messy systems. Quantum coherence has been detected in biological molecules, in photosynthesis, in bird navigation. Some researchers even speculate that quantum processes might play a role in consciousness itself. though that remains highly controversial and speculative. The point is, the quantum world isn't as far removed from everyday experience as we used to believe. And the principles that govern quantum behavior, superposition, entanglement, measurement-induced collapse, are the foundation of everything. The classical world emerges from quantum mechanics. It's all quantum all the way down. We just don't usually see it because we're too big, too warm, too noisy. So while you can't quantum freeze a pot of water, the fact that observation can freeze anything should make you pause. It should make you ask, what is observation really? In quantum mechanics, it's defined operationally. Observation is any interaction that extracts information about a system's state. It doesn't require consciousness. A photon hitting a detector counts. A particle colliding with another particle counts. The universe is constantly observing itself through these interactions, collapsing superpositions, defining states, carving reality out of the fog of quantum possibility. But we, as conscious observers, occupy a strange position in this picture. We don't just interact with quantum systems, we experience those interactions, we assign meaning. We wonder what it all means. And this brings us back to the watched pot and the psychological dimension of time perception. When you stand over that stove, staring at water that refuses to boil, you're not triggering a Quantum Zeno Effect. But you are experiencing something profound about the relationship between attention and time. Time isn't a fixed, objective thing that ticks along independent of who's experiencing it. Time is relative. Einstein taught us that much. But it's also subjective. Two people can experience the same 5 minutes in radically different ways depending on what they're doing, where they're focusing their attention, how engaged they are. A watched pot never boils because watching warps your internal clock, stretching seconds into subjective eternities. The pot boils at the same rate. But you, the observer, experience time differently. This is the human-scale echo of the Quantum Zeno Effect. Observation changes things. Not always in the physical world, but always in your experience of the world. When you pay attention to something, when you watch, when you wait, when you focus, you alter your relationship to time. You trap yourself in a kind of temporal stasis where change feels impossible because you are so acutely aware of its absence. And the only way to escape that trap is to stop watching. To let go. To trust that the process will unfold without your constant surveillance. There's a lesson here, maybe. About patience, yes, but also about the limits of control. We like to think that paying attention to something helps it along, that focus and intention can bend reality toward desired outcomes. And in some contexts, that's true. Attention drives effort, and effort produces results. But sometimes the best thing you can do is look away. To stop measuring, stop checking, stop obsessing. Because in both quantum mechanics and subjective experience, relentless observation can be a cage. It freezes the system either literally at the quantum level or subjectively in your stretched-out perception of time. The pot will boil. The process will complete. But only if you give it space, let it unfold unobserved, trust that reality doesn't require your constant witness to function. So the next time you find yourself staring at a pot, a loading bar, a clock, waiting for change that seems impossibly slow, remember, you're not just waiting, you're observing. And observation, whether quantum or psychological, has power. It shapes what you experience. It can trap you in time, make minutes feel like hours, freeze your world in a state of unchanging anticipation. But it doesn't control the pot. The water will boil, whether you're watching or not. The difference is only in how long it feels. And maybe, just maybe, the secret to making time move faster is to stop trying to catch it. To let the universe do its thing, unwatched, unmeasured, free to evolve without the weight of your gaze pinning it down. The Quantum Zeno Effect is real. Observation freezes quantum systems. But the pot? The pot will boil, eventually, probably when you're not looking.